record. All right, so our next speaker is Robbe Brants from Ghent, and he will be talking about thermalization from mode structures.
Thank you. Yeah, so in this talk, I'm going to try to explain to you how we can get some better understanding of thermalization by looking at the modes of your system. So why do you even bother looking at this in the first place? Well, if you're trying to understand something about thermalization, so how some system reaches a thermal equilibrium state, and as we approach this near equilibrium, we're also often interested in what the relevance of hydrodynamics is. There's two different approaches, in my opinion. You can either try to make some model that represents your system as accurate as possible and do some real-time simulations and try to get all the interesting features out of it. The disadvantage, of course, is like if you find these different features, it's often hard to explain where exactly these arise from. So the approach that I'm taking here is to instead look at some very simplified models that have the same features and see if we can there understand what's going on, and then go to like more and more complex models to see like which of these features remain and what conclusions we have to change. So in particular, the features I'm looking at is the dynamics and the transport properties at like the most fundamental level, which is by applying some sort of perturbation on an equilibrium state and then seeing how your system responds to it at some other point in space-time, which is given by the retarded correlation function. And because we're looking at this linear regime, it makes sense to decompose into some plane waves and calculate the Fourier transform of the correlation function, where we then apply some form of signal analysis to find the different modes in your system. So how this works exactly is that if we have our correlation function in Fourier space, but we want to know the real-time dynamics, we need to apply some inverse Fourier transform, which is given by this integral along the real axis. But if we are specifically looking for some form of thermalization where we have like different components that are decaying, it makes sense to do some analytic continuation towards the complex plane. And so what we do is we close this contour integral. This arc will typically vanish. And so this integral is then given by sum over all the different singularities in complex space, which I will also refer to as non-identities. And these are then, of course, the modes of your system. So I'm going to show by this tell you something about thermalization. Of course, if we have just a single mode, it's very trivial because we just have our correlation function in real time decaying at some exponential rate. And so this rate is given by the imaginary part of your mode. But as soon as we go to something more complex, let's say we just have two modes, this is already a non-trivial question to answer, because we now have two different contributions that are decaying exponentially, but at a different rate. And so how quickly your correlation function itself is decaying depends on at what point in time you are. So at early times, we can make some approximation where we essentially take this average, like weighted average of the two decay rates. But of course, as we go to later times, this is no longer a good approximation because this mode will start decaying much quicker than the other mode. And so this decay rate will actually start shifting and becoming slower as we go to late times. At very late times, it makes sense to just take the decay rate to be the slowest one. But then, of course, this doesn't work if, let's say, we have some sort of continuum of different modes that might reach all the way up to the real axis, because at this point, we don't have a slowest decaying mode anymore. So we need some better idea of what's going on. And this would, for example, happen if you have, let's say, some scattering process where the cross-section doesn't really have like a lower limit. For example, for 2 to the scattering, you expect some term like 1 over center of mass energy squared. So if you go to very large momenta, you don't really have any lower bound on the decay rate, no, on the time scale to which you decay. And so this has been shown to explicitly, for example, to happen in some scale theory where you have self-interacting 5 to the 4th term, but also in QCD kinetic theory. If you're looking at very large momenta, you can show to have some scaling where the relaxation time actually keeps growing indefinitely. And so if you then want to describe these sort of mode structures as well, we need to have some more general concept that describes them. And so the one I'll be using is some form of mode density, where instead of having just a sum over a discrete number of poles, we have some sort of continuum, and this sum will turn into a kind of integral over a region of complex space, where this rule gives you essentially how much each point in space is contributing towards your real-time correlation function. So this can, of course, describe all these different kind of singularities. You can still describe modes where this will depend on like the residues of each of the poles. But we can also have some branch grid where this is now a one-dimensional integral along the discontinuity. Or in the most general case, we have some general area in complex space that will have non-analytic properties, in which case this is some sort of two-dimensional area density. Here's a basic example where you essentially have some sort of toy model, which is kinetic theory with in the relaxation time approximation, where we will make our relaxation time depending on the momentum of the particles as this distribution function decays towards some equilibrium one. And the nice thing is that we can just analytically calculate what the correlation function will be and also what our mode density will be. And so here's an example where the relaxation time is proportional to momentum. Again, this is for 2-to-2 scattering processes, quite common. And for simplicity, I took this equilibrium one to be just a Boltzmann distribution, which has some exponential tail, which is quite important. Because if you remember, each of these modes here on the real axis, we have the imaginary part of frequency. Will have, like each of these particles will correspond to a mode at a location which is minus I over the relaxation time. And so if you're looking at very close to real axis, we're looking at these particles with very large momenta, and these are exponentially suppressed by the equilibrium distribution function. And so our mode density will also be suppressed towards the real axis. So even though this is technically gapless, there are modes all the way up to the real axis. We do have some effective gap coming from this exponential suppression as you get closer. We also see some sort of peak here, so you will still have some sort of definition of like what the relaxation rate will be, except for that it's not just a single rate and it will start varying throughout time evolution. So how do we quantify this? Well, what we can do is, if you remember previously, our decay rate was given simply by I times the frequency of the mode. So what we do is we now take some sort of collective decay rate where we integrate over all of the different modes weighted by this mode density, which is this rho. And so this is essentially the expectation value of your frequency of your mode. So for example, in this case, you would get some sort of value here in the middle. But what's also important is that as we start going through time evolution, these parts of these modes here will start decaying very quickly compared to this ones. And so our mode density will effectively also change throughout time evolution. And so at very late times, what we expect to see is a bunch of modes here, and then everything here is exponentially suppressed by time evolution. And so we will have a slower decay rate, which is like around this value close to where the effective gap is. And to take this into account, we simply multiply the mode density by this factor e to minus I omega t, and we now have some time-dependent decay rate. Now, what this means in terms of physics, if you remember at the start, I said we can calculate the real-time correlation function to be like this integral over all of the different modes in your system, which is this here. And so having this I omega up front here is essentially just the same as taking minus the derivative of your correlation function to time, which gives this term I omega here. And so this gamma t is at some point in time is effectively the momentaneous decay rate of your system is at this point. This doesn't necessarily tell you what your, like how much of your initial perturbation is still left in the system. But we can of course calculate it by simply taking like the average over the decay rate up to that moment in time. At this point, I want to take a moment to compare to what's often done when you're considering some hydrodynamics, which is to essentially, okay, we can have some over a bunch of different exponentially decaying modes, which in Fourier space will look like a bunch of single poles. And what we want to do is match this to some sort of single pole correlation function in the limit of frequency going to zero, because that's what we're interested in for hydrodynamics. And so what we're essentially doing there, okay, so we match the residues in order to make sure we have the proper normalization. And now what we find is that the inverse of decay rate, which is some relaxation time scale, is the weighted average of all of the inverse decay rates as well. So instead of having the decay rate as the average of all decay rates, we now have the relaxation time as average of all the relaxation times of different modes. So this does actually give a different result. Now, in terms of like interpretation, what this actually means, bit less clear. At early times, of course, it's previous decay rate at gamma 0 is better approximation because it's the exact value. But at later times, as this gamma of Blackwell's charge start changing through time, you do actually expect to have like a region where this 1 over tau pi is a fairly good approximation actually of, so what we can say about this tau pi is that this is actually some sort of decay rate of an average correlation function where you're looking at some moderate time scales. But I do think what's important to mention here is that if you go to like very late times, which is where you would actually apply hydrodynamics, this doesn't necessarily give you like the slowest decaying mode or anything, or like the correct decay rate at very late times, since this may grow much larger than 1 over tau pi. So it works at some intermediate time scales. That's what I'm going to say about it. Okay, so I previously looked at some sort of toy model in the relaxation time approximation. And I want to see how this generalizes to some form where you actually have some interpretation as a quantum field theory, which is going to be this scalar self-interacting theory. And now our collision kernel will correspond to something much more complicated where you have some scattering process. But the idea is if you're looking at a linearized level, we can always write it in this sort of more instructive form where we have a relaxation term. If you're going to do the relaxation time approximation, we only keep this term and then ignore everything else. I'll come back to how good an approximation it actually is later on. And then we have this sort of propagator term or whatever you want to call it, which contains all of the more complicated physics that's going on with these scatterings. If you're going to do some numerical calculations, it's quite useful to decompose this into spherical harmonics because we're looking at some isotropic background, so this will be diagonal. But to get some analytical insights, I actually use a slightly different approach. If we look at this F not to be, again, just classical statistics, we can actually get some analytic insights. So we can calculate this GPQ analytically in a closed form expression. And in fact, we can also invert it using this second order differential operator, which turns this previous integral equation into a differential one. I'm not going to go into the details of it, but what's important is that this is some confluent Hoyne equation, which has a couple of different singularities, and sadly there's no closed form solution. But because this occurs a lot in, for example, holography, and so we can use all the different methods that exist there to actually guess.
We go back one slide. So sorry, maybe one more slide. So this is some scalar field theory, and this you're doing. This is like Boltzmann transport on the.
Yeah, so this is like a very simplified model, I suppose, where you do some kinetic theory, which is 2-to-2 scattering with like a constant coupling term, and yeah, and then you linearize for your kinetic theory.
So the like the how do you say the equilibrium distribution function is it's like the Maxwell-Boltzmann.
Yes. So, but this is basically a choice that I made here because there we get these analytical insights. You can do this for any other one, but there often you have to rely on some form of numerics. But a lot of the conclusions will be really similar.
And in the Boltzmann, you're taking energy to be proportional to.
Right. Okay. So this would be massless. Yes, I forgot to mention that. That's indeed quite important as well. Yeah. Okay. Yeah, indeed. That's how we end up with some form of exponential term instead of something that's much more complicated. Right. So essentially, what's important is that we have some sort of boundary conditions because this function can turn singular at certain points, which are 0, infinity, and 1 over I omega, which is like a special point on convective. But we need to have it regular at 0 and infinity in order to have things like finite energy. And what you would typically do in holography is to set the source to 0 and see if there's any solutions. This would be then the quasi-normal modes of your system. And it turns out for this specific case, there are no solutions. So then the question is, where do the modes in our system actually come from? And the answer lies in this additional singularity here at 1 over I omega, because depending on which side of the imaginary axis we are, the singularity will lie either above or below the axis in complex momentum space. So the idea is we have some sort of solution, which is the response of your system to the source. And if you're looking at, let's say, like energy or whatever that we're tracking through space-time, we'll have some integral along the real axis of momentum, and so this value will behave discontinuously depending on which part of complex frequency space we are. So skipping over some of the more complicated calculations, we can calculate this mode density based on these confluent Hoyne functions and some connection formulas. And we find this result where I compare it to the RTA approximation where you just get this term. So firstly, I want to say, I feel like the RTA approximation is really bad here. Because firstly, the relaxation rate is like much slower. We're really close to the real axis for this one. And also it's much more narrowly peaked, which is quite nice because it means we can just use like a single relaxation rate and get a very good approximation over like a wide range of length scales, time scales. But I also want to mention that the fact that this is like so steep here might actually be a result of having this simplified model. And I believe that for like more numerical, if you do some numerical analysis on like a more realistic model, this might not be as extreme as you find here. It would probably lie somewhere in between these two. But it also tells us that like thermalization is really much more complicated than you might initially expect, because like a lot of the times I see just using like the relaxation time approximation but this is not necessarily an accurate representation of your system. That's all here. Now, what I would often do now is look at what happens if you have some inhomogeneities in the system. Now I was just looking at time and frequency, but you can have some sort of wave factor. But I think what's actually more instructive here is to look in real space, if you can see decay here. And in particular, I want to be focusing a bit on the hydrodynamic aspect, which was just completely neglected previously because I was just the mode at frequency equals 0. In particular, I want to look at what happens if we follow the fluid along some radial line in the light cone diagram. So we choose some velocity v and look at the position of space which is traveling along at this with the response function at this velocity. So here's a very simple example for diffusion where our dispersion relation for the hydrodynamic one is just minus I dk squared. We can compute the correlation function in real space analytically. And now we just replace this x by velocity times phi. And what you see is that you have some exponential decay along this radial line, depending on the velocity v. So there's like a direct analog between having your mode become dissipative at finite gradients and having a decay rate depending on the velocity within your light cone. So here I just had an analytic expression, but usually this is, if you're looking at a more complicated dispersion relation, we don't actually know what the real space correlation function looks like analytically. So how we would calculate it is by, so this is the definition of your correlation function in real space and time with this velocity v. And we can actually see this as some sort of an action depending on velocity and the wave factor. And we continue this to complex space where we compute this decay rate with some saddle point approximation. But the main point is this is actually not that hard to compute for like a lot of different dispersion relations. You can actually just get like closed form solutions for this gamma. So why is this relevant if you're looking at comparison between hydrodynamics and non-hydrodynamics? Well, if you think about something like causality, where we know that where we see that, for example, in the diffusive case, which is what I'm showing here, you actually have like some spread outside of the light cone. What we see is that we need some sort of additional modes that cancel this contribution outside of the light cone in a certain way. But these additional non-hydrodynamic modes cannot decay too quickly because that means that they couldn't cancel it outside of here. So we essentially look at what's the minimal decay rate of your hydrodynamic mode outside of the light cone and use this to put, for example, a lower bound on the relaxation time scale of your non-hydrodynamic modes in order to be able to cancel this contribution. So that's what I'm showing here. So this is, for example, where you have like a constant relaxation time approximation where everything's just decaying at a certain rate. And essentially, if you would put this non-hydrodynamic mode any deeper into the complex space plane, it would have a decay rate that's higher, and so it wouldn't be able to cancel the diffusive mode at v larger than 1, smaller than -1. Similarly, this is for the target first equation, or Israel-Stewart, or whatever you want to call this, where you essentially just have a single mode approximation. You also see that you have now two modes which will cancel each other exactly when you're outside of the light cone. But once again, you can't put this non-hierarchical mode too deep into the complex space, because then otherwise your theory would start violating causality. This also allows for like a very nice comparison between these simplified, like more phenomenological models and, for example, holography, which I'm looking at here. So for holography, what happens is that we have these additional non-hierarchical modes that will actually get closer and closer to the real axis as you go to large wave vectors. This large K. And as a result of this, if you actually go close to the edge of the light cone, these non-hierarchical modes will actually start decaying slower and slower. And eventually, if you're right at the edge, they actually don't decay anymore, at least not exponentially. There will, of course, still be some polynomial decay. But this happens very slowly. And the reason is that this approach to the real axis happens with a power k to the minus 1/3. And this leads to having like power 1/4 here. And so you have to be really close to the light cone in order for to have this decay rate on non-hierarchical modes go to 0. And so in fact, even though there's this small part near the light cone, which is actually not behaving hydrodynamically at late times, we still have a very high decay rate if you look, for example, close to the center of the light cone here, as compared to, like, let's say, this RTA approximation or Taylor-Fritz equation. So the statement that, for example, in holography and strongly coupled system, we have quick thermalization mostly talks about essentially this decay rate here at the center of the light cone. Okay, that's it for my talk. I think the main takeaway points here are that thermalization is really not as simple as one might think at first glance, and we can't just look at some single decay rate and expect to properly explain all the physics in our system. In general, we actually expect it to slow down over time as we get closer and closer to a thermal state. We actually have slower thermalization. I didn't talk about this that much here, but this will also, of course, also depend on the gradients that we have in our system and so on. Like our hierarchical modes will also start decaying, and which leads in real space to also a decay rate depending on the velocity along which you're tracking your fluid. So finally, for future work, I do also want to look at what happens, for example, in QCD kinetic theory to see like which of these conclusions for scalar theory actually generalize. And finally, this is what I'm working on now, which is use causality in combination with this exponential decay rate in real space to actually put these sort of bounds on the non-hydrodynamic sector. That's it. Thank you.
We have time for a couple questions.
Maybe I guess you didn't really talk much about like branch cuts in the.
Which type of branch cuts? Because like these ones like are the discontinuity across a vertical branch cut.
Oh, I see.
That's this. So okay, so I explained this extremely briefly, but the idea is we look at two different sides of the imaginary axis. The singularity will lie at different sides of the real line in momentum, complex momentum space, and so we end up with a discontinuity in the Green's function, which is what this branch cut along the imaginary axis is, essentially.
So let's see. But in terms of, let's say, this row is like kind of the density of.
Yes.
So a branch cut would mean what for?
Discontinuity.
Discontinuity.
Yeah. So for so these were like the different cases that I looked at. So for if you have single poles, this will be a sum over residues. For a branch cut, this is directly just a discontinuity. And then, kind of more general cases where it's two-dimensional. So somehow I'm under this impression that so poles will lead to kind of exponential decay, but branch cuts, they lead to like kind of power law decay. Well, it depends a bit on what kind of branch cut you have and how it's. For example, I think what you're mostly looking at it then is late time expansion.
Yes.
So if you're if this density goes to as a power law to 0 here, well, or not to zero, I guess. Point is, if it's like at small frequency, if this is also a power law, you will get power law behavior in real time. In this case, you have this exponential suppression. And what this actually will look like at late times is that you will have a sub-exponential factor. So for example, here we have this term e to the minus 1 over the imaginary part of the, and what this will lead to in real time is some e to the minus square root t, for example. So this doesn't have to be a power law, it will typically be something between not decaying and a exponential. But also, because as you can see, like there's essentially a gap here at late times, it will be almost exponential. It's just that if you go to stupidly late times, I'm talking like thousands of times your relaxation time scale, you will notice that it's actually still slowing down.
Okay, if there are no more questions, let's